up with new business models in order to support these grassroots craft industries. So with that, I'll just turn my video on once more, so hopefully the connection doesn't come out. But I wanted to thank you, and I hope that I get to be a part of any future plans of yours academically. So thank you, Namaskar.
Namaskar. Thank you so much, Jeremy Fridjan. We are very, very glad to know about all your experiences. A student in psychology, and now here going to the whole world, now in Assam, going to our silk industry and bamboo and cane. And actually, it was, if our students would have been present here, it would have been very useful for them to know what a true entrepreneur is. That is what you have been doing, helping the grassroots level artisans and showing them what can be done through the various technologies available. You had helped a dying art of a town, and now they have found a platform which is so much useful for them. I'm talking of Bagru, and of course I know you would be helping people who would ask help from you, and surely in the future we would like to interact with you, and also you may be doing something with our students, helping them out, and with your words they would really be inspired. Thank you so much for being here, and we hope we will be meeting soon in the near future. Thank you so much.
My pleasure. Thank you too.
We at Nagaon Polytechnic are extremely honored to have Professor Amitava Ghosh as the chief guest of this valedictory session of the week-long online program. A researcher, administrator, and educator, he currently holds the position of Honorary Scientist, Indian National Science Academy, New Delhi, and Honorary Distinguished Professor in the Aerospace Engineering and Applied Mechanics Department at the Indian Institute of Engineering, Science and Technology, Shivpur, Howrah, West Bengal, and also Platinum Jubilee Senior Scientist of the National Academy of Sciences, India. Professor Ghosh has made extensive contribution in various fields, including fundamental and applied research, technology development, administration, and social development. We are deeply honored to welcome you to deliver your speech. Sir, the stage is yours.
Thank you very much, Professor Saikia.
Thank you.
Professor Valediction, who brought me into this, the Honorable Principal of Nagaon Polytechnic, Professor Varali, the members of the organizing committee, the distinguished members of the guests, and my dear participants. I think I feel very happy to attend this event because Nagaon Polytechnic, being such a institute in one corner of the country, can draw the attention of the whole nation through this online program, is really a commendable job. I congratulate the organizers and taking this bold step in spite of your limited facilities and to take up this task of organizing such a program. I told Professor Dixit that, though I am teaching for almost 56 years now, but I still have not come up to the level of becoming an educationist, I can call. I am still a simple teacher, and so whenever it becomes a task of talking of education, I feel very hesitant. But I think I could say no to Professor Dixit because he is one of my most beloved former student and a very respected colleague at present. So therefore, what I was thinking that if I have to say something, one thing I always keep it in my mind, being a very old teacher, that if I say something and at least a section of the audience, if they don't find that they have been benefited a little bit through that talk, then it is better not to talk. So I thought that since I am not an expert in education, and these terms like outcome-based education, etc., was not very familiar with me, I decided to talk on one topic which I thought that may be useful to my young participants who are young teachers at various institutions. So I thought that I will talk on the subject, what is the engineering and technology, and certain fundamental issues related with these two branches of studies and their interrelation with basic science. So I think as it happens for any teacher that he would, like me, either would like to take the blackboard and chalk, or if he is a little bit aggressive one, he will share the slides. So I will take the liberty of sharing my slides if you permit.
Yes, sir. Yeah. Bhavali, you just, yeah. Yes, okay. Yeah, it's visible. Yeah.
Can you see the slides?
Yes, sir. Yes. Yeah.
Yes, sir, we can see this.
Okay.
You can go to full screen. Yes. Okay. Yeah. Yeah.
Now it is.
You can see the slides and you can hear me also.
Yes.
So I will start.
Yes.
And I am sorry that I am crossing the limit. That means I was supposed
So you take the time. We can extend the session by 20-30 minutes. Okay, no problem.
Okay then. Okay. Thank you. Thank you.
Okay.
And with the permission of Professor Varali and Professor Saikia, I think I'll just try to do as much as possible. So let us understand engineering education and certain fundamental issues. Now, I think in order to chart out a correct and desirable path for the outcome-based engineering and technical education, it is essential to have a very clear idea about the basic distinctive features of science, engineering, and technology. This is because I have found that often these terms are intermixed and many may not have a very clear idea about the correct meanings of these terms, their proper distinctions, and for their relevance to the society. So, for example, I will show you a slide which will show you the common misconception and bias, mental bias, in the general public and also in media. See, we have seen this kind of pictures. On the upper part, you see that a rocket is going up, crossing the sky, blazing through the sky, and the caption will be a triumph of science. But sometimes, very unfortunately, you can see something like what is shown below, and then invariably the caption is going to be failure of technology. So this is what is very wrong, and I am just going to explain now what exactly science, engineering, and technology means with the help of a very concrete example. And so therefore, you should also know the hierarchy that, of course, at the very first comes science. And from science we come to engineering. And from engineering, finally, we reach the level of technology. Now, what are these terms and what are their meanings, and can we get some examples? Now, science. The word science originates from the Latin word scientia, which means knowledge or knowing, creation of new knowledge, having newer understanding and such things about nature. An example we can give you, like say, spontaneous and stimulated emission of radiation. I am quite sure, being man of technology, all of you have heard about these two terms. What does it mean is that if you see this one, that if there is an electron at a higher energy level, then it can spontaneously come down to a lower level of energy, and this extra energy which it has lost, it radiates in the form of a photon whose energy is h, Planck's constant, into nu, the frequency. You all know that. So this particular phenomena in nature is called spontaneous emission of radiation. But scientists discovered, this is a part of science and scientists' job to discover this, that if a particular electron is at a higher energy level here at the level E2, and there is another photon which is coming and passing nearby, whose energy is exactly same as the difference between this energy level here, energy level there. What happens then? Then this photon or this electron also comes down, radiating exactly an identical photon, h nu, and this kind of radiation is called stimulated emission. And therefore, you can create two photons of exactly same frequency, same phase, everything. That means they are coherent photons. Now, this is a natural phenomenon the scientists, more particularly speaking, physicists have discovered. Now, this is called science. Now, it has absolutely no usefulness unless we manipulate it. Now, therefore, next term is engineering. The term engineering originates from the Latin word ingeniare, which means to innovate, to contrive, to devise. Such creations come from basic science. It is also related to the Latin word ingenium, which implies cleverness. Thus, when the basic science of stimulated emission is employed for practical purposes, we get something what we call laser. It is light amplification by stimulated emission of radiation, which you are all familiar with. So once science discovers the phenomenon of stimulated emission of radiation, it is engineering which conceives a method to transform this knowledge into something that can be effectively utilized. The next slide shows the engineering through which we get laser. So here what happens, such a photon gets emitted, and there are two photons then through stimulated emission. Then what is done? There are two parallel mirrors. One mirror is a full mirror, other is a partial mirror. So then these photons reflect back and forth again and again and again. And in the process, they stimulate more and more photons. Ultimately, an extremely powerful beam of coherent photons come out, piercing through this partial solid. So this very strong beam, which you all know, is called a laser beam. Now, this is a product of engineering. It has been obtained by proper, clever manipulation of a scientific phenomena like stimulated emission. But the next step is what you can do with this powerful beam. It can be applied to many areas, and that is the job of technology. Now, this word technology originates from the Greek word technologia, which means systematic use of craft, art, etc. It is also related to the Sanskrit word taksan, which means carpenter. In Greek also, tekton means carpenter. And I think that the term dakshata, that is skill, also originates from the same root. So technology once uses this extremely powerful coherent beam of light, which you call laser, and we use it for many things like manufacturing, communication, material processing, etc. And this is called technology. We use this powerful beam and we use it or we apply it to various areas of practical use. It could be manufacturing, it could be communication, it could be processing, it could be many other things. And that part of that activity we call as technology. So therefore, I believe that this terms science, engineering, and technology, they are very different. They have distinctiveness or distinctive characters. So when you find many places, there are sometimes it is called that instead of engineering and technology, most often what happens, the people are not very sure about what does it mean. What part is engineering and what part is technology? Now, of course, we have to remember that it is technology which is the driving force behind the growth of world economy and the progress of civilization. Pure knowledge cannot give us material benefit. Of course, it can give us philosophical benefit, philosophical uplifting and such things. But if we come down to the ground level of the economy of our country, then it has to be technology. Now, with this little introductory note on science, engineering, and technology, we can proceed to make further distinction between the characters of these areas of activity like science, engineering, and technology that may help in grasping some fundamental issues related to engineering education on which we are interested at present. Say, for example, science. What is the basic feature of science? Basic feature of science is analysis. Analysis and understanding of some natural phenomena. It requires the capability to observe and understand. So therefore, this is what is science. You understand nature, discover some phenomena through analysis and such things. On the other hand, engineering represents synthesis. It is the basic feature is synthesis using various different disciplines, different phenomena, different activities into one thing and using the capability to manipulate. And so therefore engineering and science, they are very opposite in nature. One is analysis, one is synthesis. And the outcome are also different. So for example, in science, the output is new knowledge and better understanding of a known knowledge. On the other hand, engineering is outputs are products, both physical and non-physical. So therefore, again, science gives us knowledge, understanding, whereas engineering gives us actual, real, usable things, which we produce by taking the material offered by our Mother Earth in the form of raw material. So therefore, I hope that the science engineering we should not mix up. So therefore, in one case, when the rocket is going up, we call twinkle of science. When it is falling down, it is failure of technology. That is not the case. And also a very popular image of science and engineering, the difference I have tried to depict through this slide. It's a very popular image, but of course I must say that to partial it is true. So science is an activity which is based on ivory tower, not much connected with the rest of the society. On the other hand, engineering is represented by a work table where you have to work hard and also you have to deliver goods. Now, engineering was in education. What happened, if you look into the history of our science and technology education universities in Europe, engineering was dealing from science and had the typical characteristics of craft, and the education was based purely on training and practice in the workshops. Universities did not entertain academic programs on topics we consider as engineering today. For example, not very far back in the past, you have perhaps heard, those who are in manufacturing, the name of Tobias. Tobias was a very famous person in manufacturing science, particularly in metal cutting area. So when you came to Cambridge University to do PhD on machining, so the university authorities told him that we don't do such things in this university, go out. Of course, later he could manage to get admission and became a very famous professor of Cambridge in the area of machining science at a later time. But that was the earlier attitude. Those engineering and technology were not a part of university education. And the university did not entertain academic programs on topics we consider as engineering today. So if you go back 100 years back, you will find that engineering or technological subjects are not present in the university curriculum. Of course, there are some exceptions. Brilliant men like Leonardo da Vinci, who had both command on engineering and science, but application of scientific principles and methods to engineering started once the first industrial revolution took place in late 18th century with the invention of steam engine. Then only it became important that science and engineering cannot be delinked, because once the steam engines came into, they had to improve their performance, wanted to understand the science of heat or thermodynamics, one had to understand kinematics, one had to understand many other areas. So therefore, only then it became clear to people that engineering education and science education can be dealing. Now, interestingly, this was also the time when the old science was being replaced by new science, and the rapid progress was being made in all areas of science. So this is a thing, what happened, they actually made their journey together. And this necessitated starting regular engineering programs as a part of university education. Earlier, they were only through practical trainings and workshop trainings in the factories and their training centers. Now, I think in the early days, the engineering activities which were predominant were mineral excavation that goes on since time immemorial, long back, even 5,000 years back, people used to extract material. Then metal extraction through different processes like smelting, melting, so on. That is also a very old activity, going back to thousands of years. Building and other construction. Now, if you see the kind of building and other construction activities in our even Indus Valley civilization, you'll see how developed they were. Making machines and weapons for warfare. This machine making was predominantly for warfare in those days. Building ships and carriages, that was partially business and partially warfare and conquering other countries. And of course, another area was textile. These are the old activities which we may call a part of engineering and technology, which are going on even since before the Industrial Revolution. Actually, as a should I can mention, in 1753, John Smeaton, a designer and builder of Thomas Newcomen's atmospheric engines, first identified those areas of activities which were for the benefit of the civilian population as civil engineering. Because he found that lots of activities engineers and they are actually not meant for warfare, they are for civil population. Then he branded this group of activities as civil engineering. All others were grouped under one common heading as military engineering. Therefore, the whole of engineering was divided into two classes, apart from mineral excavation, metal extraction, etc., as civil engineering and military engineering. Now, the advancement of science and more inputs from scientific discoveries caused the military engineering to expand and proliferate, giving birth to many new engineering branches as we see today. Say mining, metallurgy, and civil engineering maintain their old names and identities even today. You can see here that they are continuing as before, but military engineering first got proliferated to electrical engineering and mechanical engineering. Then mechanical engineering got proliferated into aerospace engineering, chemical engineering, and mechanical engineering continued. Electrical engineering continued as a discipline, but when it got intermixed with physics, then we got electronics. And then when mathematics got mixed up with this, we got computer engineering. And of course, electronics also gave birth to another discipline we call communication engineering. Now, so there are more and more science here. You should know that this is happening because when in the 19th century, after Maxwell and Faraday, when electricity and magnetism achieved certain degree of maturity, electrical engineering became a separate branch. Some of you may know, but I know even in our time, maybe a few batches before me, 7-4, maybe 10 years senior to me, those people in BHU, they used to get a combined degree of mechanical and electrical engineering. Then mechanical engineering and chemical engineering and aerospace engineering were the same subject and taught by the same department even today. So, like mechanical and aerospace engineering is a combined department even today in many of the North American universities. In many European universities, chemical engineering and mechanical engineering, they are same. And even if you go to US, even today, the electrical and computer science and electronics, they are all in the same department. They call it EECS. Even university like University of Michigan, they don't have separate departments. So the next slide, what I'll do this, what I mentioned so far, that the progress of science, how it is leading to the proliferation of original military engineering into the modern branches of engineering, that I will explain in more details. The objective of this discussion is that those who are planning to develop new curriculum and not to depend all the time on age-old curricula, so to have new ideas, it is always necessary to have some clear idea about the way these engineering subjects have evolved. That is very important. Then only you can project in future if you know the past. So therefore, past is necessary to be known if you have to project for the future requirement. So you can see this, like originally we had subjects like if you call as engineering subject of course, basic engineering, mechanics and thermodynamics. Mechanics and thermodynamics in a combined manner, that is military and mechanical engineering, whereas it is predominantly mechanics which is civil engineering. And later materials technology became a part and civil engineering continued like this. Now, when electricity magnetism as a subject matured in the 19th century, then we had a separate branch like electrical engineering. When modern physics, that is quantum mechanics and atomic physics, electrons became known and their science became known, then it got proliferated into two branches. One is electrical engineering and electronics. Then came math. When math got mixed up, it gave rise to two different, from electronics and math, gave to communication engineering and computer engineering, and of course, electronics is continuing. On the other hand, mechanical engineering, it got mixed up with chemistry and gave birth to chemical engineering. Mechanical engineering still is continuing, and also aerospace engineering separated because it became a very major activity, though I must remind you that mechanical and aerospace engineering is still one department in many of the very well-known famous universities in North America, like even Montreal. McGill University, they have the same department, mechanical and aerospace, no two departments. Then in chemistry and civil engineering, they gave rise to another branch we call today environmental engineering. And then life science is the latest in progress. And when it comes, and chemical engineering and life science combined, they become biotechnology. So this is the way the progress of science, basic science, and progress of engineering, they are interlinked. So therefore, whenever we plan or we want to design curricula, it is very important that we should keep in mind that they are not separate. So there are many places I have noted in many engineering colleges, basic science is not important. We are going to treat our students into engineering or technology. Please remember that innovation, what we talk so much about these days, we must be innovative, we must innovate, we must make in India, all those things, It is possible only when real good scientific background or scientific foundation of the engineering and technological subjects are understood clearly. Devoid of basic science, no engineering innovation is possible. I mean, it's right kind of some kind of tinkering or what we call in India is jugaad, that may be possible. But with that, you cannot conquer the world market. To conquer the world market, to become a central stage player in world economy, you have to make your products truly good, competitive, and of better quality and better performance. And for that, you must improve on the very fundamentals, that is the basic science. Without that, we will always followers. You can only copy, you can do a little bit of reverse engineering, and so on. But to become the true leaders in the field of technology and engineering, it is not possible unless the foundation in the science and fundamental basic engineering science subjects are strong. That's why I propose that when you design, if you want to really make your students truly competitive and truly effective for the new era which we are going to face very soon, you must train them in areas so that they have this innovative mind and they can innovate and they can improve. All those things will be possible if you train them also very strongly in some basic fundamentals, to the extent possible, of course. But delinking science from engineering and technology is disastrous and leads to you creating only some, I'll say what, some just laborers, nothing else. And I think a suitable structure of engineering and technology educational program is diagrammatically shown below. It shows the basic foundations and the secondary and tertiary level subjects at their appropriate position. So like say, for example, we must have in our whole curriculum at the bottom, at the foundation, two types of foundation. One is foundation in basic sciences, like physics, chemistry, mathematics, life science, material science, and so on. And here, Newtonian mechanics, these are the engineering science subjects, which we call core subjects. Thermodynamics, solid mechanics, fluid mechanics, electricity and magnetism, and maybe materials a little bit. So, and mathematics is of course always there. Now, if you train very strongly in these subjects, Newtonian mechanics, thermodynamics, solid mechanics, fluid mechanics, electricity, magnetism, he can be an excellent mechanical engineer or aerospace engineer anywhere in the world. You don't have to bother. Once we were having a meeting during our Indo-US collaborative center program we are having in Chicago, we had a meeting with a lot of industry people. And then I think the discussion was that what kind of engineers the industries expect. I'll tell you the contrasting view of Indian industry people and American industry people. Here, if you go into curriculum development, if you have a discussion with the industry people, there will be very serious difficulty. Now, somebody will come from a thermal power plant. He said, you must teach boilers, this, that, power plant engineering, all those things very thoroughly. If somebody is coming from automobile industry, he said, what kind of mechanical engineers are produced? He must have a very thorough understanding of automobile engineering, this, that. If you are going to have somebody from manufacturing industry, you will again have a similar view. So therefore, it becomes impossible to satisfy people of industry in that form. And therefore, what happens, all the time the industry said, no, your engineers are useless. On the other hand, when we discussed with a group of about at least 25 or 26 industries came to Chicago to have that meeting, they said in one unique voice, all of them, they said, we want you to supply those people, those young minds who has very strong background in fundamentals and capability to analyze, observe, and innovate. Nothing else. We will make them engineers. So therefore, to expect that somebody will become an outstanding automobile engineer in a college or an outstanding thermal power plant engineer in the undergraduate program or an excellent manufacturing engineer, it is absolutely absurd. They told. They said, it is impossible, you cannot do that. You train them in basic fundamentals. We will make them according to our need. If somebody joins the automobile industry, he will be trained like automobile. Now, these kind of things, what happens that after this basic the brand specific specialization, then a civil engineer can become an environmental engineer, they call geotechnical engineer or soil engineering people, or a structural engineer, like that. And at that stage, there should be also practical exposure to their specific branches of engineering, as it is done in medical education. Internship is a must, without which you cannot get a doctor's certificate. In engineering also, I believe a practical exposure, at least one semester practical exposure in an industry in a formal way is a must. So this is the way I think a subject like engineering can be taught, which will make our engineers suitable for the coming challenges which India will face, and they will also surely take our country to take a center stage role, to play a center stage role, particularly when the third industrial revolution arrives. So I think it is somewhat important for the designers of engineering and technology curricula to possess a glimpse of the process through which the engineering and technology branches have evolved. That is the way they can have some idea or inkling about how it will be in the future. It is also very essential for the students of engineering and technology to be aware of the roots of their respective branches of study. It is very important to have a clear idea of the roots. And I hope that it's a very brief introduction, but as I told you at the very beginning, I confess that I cannot talk much about education, pedagogy, etc. But I could at least tell something little about the subjects like engineering, the way I have seen it. Thank you very much for your kind attention, and wish you a very happy 2021, free from COVID, with full of prosperity and good health. Thank you very much.
Your presence has made this session and the entire program a grand success. Thank you all.
So Uday, thank you very much for bringing me to Nagaon Polytechnic.
Yes, sir, it was very good. Yeah, last lecture was fantastic. I think participants might have benefited a lot because of this one. Yeah.
I don't know. I had to arrange a little bit. And Professor Bharali, thank you for kindly inviting me and giving me a place in your event. And I'm very thankful, and I congratulate you because you took a very bold decision, because organizing such an event for a small institution with limited resources is no joke. I know, I understand that. But I really salute you for your courage and your wonderful program. Professor Saikia, thank you very much for wonderful anchoring. And you never know, if ever luck permits, I may visit your Polytechnic someday.
Sure.
Okay, thank you. Have a nice year.